Okay, so we left off yesterday looking at sine in GeoGebra, controlling all of these different values with sliders, and we finally came to the conclusion that this is the best way to write a sine equation. So that way I can just look at it and tell you what A is, what B is, what C is, what D is, and those numbers actually tell me something about how to transform it, right? So, if we have something like 3 sine of 2x minus 5 plus 4, how would you graph that? You start with the parent, no, without your calculator, you know that. Again, don't be obnoxious on purpose. So you start with the parent function y equals sine x, and what do we then do to that parent function to graph what you see up here in blue? So we want to vertically stretch it by 3. Great. Which, by the way, is going to change the what of the sine graph? Amplitude. The amplitude is now going to be 3. Shoot.
Wow.
Okay, so a vertical stretch by 3 will change the amplitude of the sine graph to be 3. Agreed? Yes. Okay, what else do we do to the parent function? Well, give me the transformations in our typical order, which is all stretches first. Then there's going to be a horizontal squash by 2. Right? Remember, horizontals are backwards. So that is going to squash it in. You could call that a stretch by 1/2. Right? Okay, but I choose to use the word that actually describes what's happening. And so that's a squash by 2. What does that change for the graph? What is the period? If we take the parent function sine, which by the way, the parent function sine has a period of what? 2 pi. If we take that and squash it in by 2, what is the period of this graph going to be? Just pi. Because this right here is the number 2. B. Your horizontals are always backwards.
So negative.
If it's negative, it's a reflection. If it's a number between 0 and 1, a decimal, that's a stretch. If that were a negative 2, it's still a squash by 2, but the negative causes it to reflect through which axis? The y. Okay, what else do we do to the graph? You're going to shift it right 5 and up 4. Okay? That was when it was written as, so that was if you had it written as 3 sine 2x minus 10, that 10 is not actually how much it's being shifted by. Okay? But, so that's why we decided we're going to rewrite them like this from now on, and so therefore I can look at it, see the number 5, and that is actually how much I'm shifting by. Okay? So what is A in this equation? 3. What is B? What is D? What is C? Positive 5. Okay? And you're shifting in a positive direction, which is to the right. Okay? Because see, we're writing it as x minus c. So this is x minus positive 5. Right? If you had something like, if you had sine of x plus 7, what is c for this problem? Negative 7. That is x minus -7. Okay? Just because that's how we're gonna graph. We're gonna take the parent and we're gonna transform it. Okay? Now, the way we actually do this is how I typically graph first. I actually don't usually graph the parent right away. Okay? Instead of just straight graphing the parent function and then transforming it, I usually use this information I'm looking at to figure out how to label my X and Y axes. Okay? Because that's really the toughest part. Typically, you look at the period to determine how you label your X-axis, your vertical line. Sometimes, however, this is a perfect example. The period is pi, and I'm shifting it to the right 5. That's going to be really ugly and hard to graph, isn't it? And I would say for an example like this, there's nothing you can do to get around it. You're just going to have to plot points that aren't going to be at the intersections of grid lines, and that's fine. Okay? Sometimes your horizontal squash might change the period, and your horizontal shift they won't line up nicely, but you can still actually fix that by being creative in how you label your axes. This is an example. It doesn't matter how you label your axes. When you shift that thing to the right 5, you're no longer going to have points on the intersections of grid lines, and so you're going to have to do it. Let's actually graph this one, because this one's a little bit challenging. Okay? So how do we use the period to determine typically how we want to break up the number line? Here's what one complete cycle looks like in sine. Okay, this might represent one complete oscillation of our pendulum, right? There's essentially 4 sections to this graph. Okay? There's this section where the graph is increasing, but it is what we call concave down. Okay? There is this section where the graph is decreasing, but it is still concave down. We have this section where the graph is still decreasing, but it has actually switched to concave up. And then we have this section here where the graph is now increasing, but it is still concave up. This terminology, increasing, decreasing, and concave up, concave down, the concavity, that's something you're going to study in good detail next year in calculus. I'm not going to ask you questions about where is it increasing, where is it decreasing, what's the concavity. But it is something interesting to think about. Let's say this graph right here represents the distance of something, like a pendulum. How far is a pendulum from its middle equilibrium point? Okay? Increasing and decreasing is describing the pendulum's what? If distance is increasing, then what can you tell me about that object? Its velocity. What does concavity of a distance graph tell you? It's acceleration. Okay? So when we first let go of this pendulum, its distance is increasing, so its velocity is positive, but its distance is concave down. Therefore, it is actually decelerating. Its acceleration is negative. So positive velocity, right, when you first let go, that's actually not when we first let go, is it? When you first let go is when you're at the top of the hill. This would be, you're swinging through that middle point. Okay? So you've got this really high velocity, but you're starting to slow down as you approach the other extreme endpoint. You change direction, so now your velocity is the opposite now, the negative velocity now, but you're accelerating. Gravity's accelerating you down to that middle point, of which you start to slow down, but you're still in the negative velocity. You're still moving to the right, but it slows you down to a stop, you change direction, and now you start accelerating back. And so that's some of the stuff you'll study in calculus, the concept of slope being velocity and concavity being acceleration and all kinds of fun stuff. Well, we break this into four sections. So we have our important points we graph, which also are important in calculus, 5 important points per cycle, 4 separate regions. So since the width of one cycle is our period, we typically want to take our period and just straight divide it by 4. So if we wanted to graph this function right here, what would the width of each of those segments of the cycle be? Pi fourths. And so what I would typically do is label my axes by pi fourths. So here's 0, pi fourths, pi halves, 3 pi fourths, pi, 5 pi fourths, 3 pi halves, 7 pi fourths, 2 pi. Oh, did it? Sure didn't sound like it to me. Okay. Huh?
If you ever remind me to go, just tell me again.
Okay. So that's how I would label the x-axis, and then the y-axis, for being vertically stretched by 3, I'd probably label by ones. 1, 2, 3. So that's it. So, great. So if you wanted to start with your parent function, which I don't expect a lot of you to, your parent function would look like this. Okay? Notice that's pretty different than when we graphed sine yesterday, and the reason it looks different is because we're labeling our axes different, which is going to kind of stretch and skew the way it looks. Right? These are, we see these on our paper as squares, but the reality is these aren't squares. This is about a 0.75 by 1. This is kind of taller. So we're seeing this vertical like squishing or horizontal stretching effect on the way this graph looks. Okay? But that's our parent function, agreed? Now I need to vertically stretch by 3, horizontally squash by 2. Whoa, that's terrible. Wow. All right. Then I need to shift that right 5 and up 4. The shifting up 4 is great because I chose to label my y-axis as 1. But the shifting right 5, that's going to be a mess. Where is 5 on this x-axis? Right? I've got to find where 5 is. I know this is 3.14. This is 6.28. What's 3 pi halves? A little bit larger than 4.5. 5 is probably like somewhere like right here. So this point here has to be shifted all the way over to here. So what I would do in a situation like this, plot that point and maybe label it as 5. Right? And then I can go, that's just a shift to the right 5. We then still have to shift up 4. Okay? And so this is what I'm going to do. I've got that point right there. I know that my next point is going to be right 1 up 3. Because that's what I'm looking at here. Right? The next one is going to be right 1 down 3. Right 1 down 3 again. Right 1 up 3. And so you're going to have a graph that looks a little something like. Yeah, something like that. And it goes on forever and ever and ever. What's that? No, typically I try to make some that are nice. And every once in a while you'll get an annoying one. Like every once in a while I get an annoying student. You know, there's 28 students in class.
See, knowing one just looking at it like, this is easy.
I'm not teasing. All right. Okay, so let's go to a significantly easier one. We started with a fairly difficult one. How about y equals sine of 1/2 x? So how might you label your x-axes? What is the period of this function? 4 pi. This is a horizontal stretch by 2, right? The graph is getting horizontally stretched. So the period is going to be 4 pi. So how much would you recommend labeling all of your x-axes by? Pi. So I might label this right here, pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi. Okay? And then we can go up by 1s on the y-axis. Agreed? Agreed. And so basically, all we got to do is go through here, and that's it. So you don't always have to start with the parent. In fact, if it's one of those graphs, you can easily label your axes. This perfect amount that just works. Labeling your axes is the hardest part, and you just draw your graph through there. Okay, that's it. There's a graph of sine 1/2 x. Now the reality is this graph has been horizontally stretched by 2. So would you describe these hills as tall and narrow, short and long, or medium? They are short and long hills. Okay? Just because they don't look like it doesn't mean they are, right? How do you know these hills are actually long and not very tall? No. Yeah, I guess. It's not imagination, it's your spatial reason. To me, your imagination is when you make up things in your head that don't exist. But for me, I'm a friend. I got lots of friends in my imagination. Okay, but no, you look at this square. This is a pi by 1 square. So this is a square that's 1 unit high, but it is actually pi units long. Okay? So clearly this is not the way this graph actually looks. It's a period of 4 pi. It's being horizontally stretched. Sometimes you'll get a graph that looks like it's these really tall hills. I mean, heck, look here, let me show you. Did I click it? This was great. It's version 4.0. So let's do something like, I'm going to graph y equals sine of 0.1x. That's sine horizontally stretched by how much? Ten. Okay, look at that. Right? Now, I'm not going to change the graph at all. I'm just going to change how I label the axes. So would you describe these hills as narrow and tall or long and short?
Long and short.
They are long and short, right? If you make your axes go up by 50s on the x-axis, but 0.2s on the y-axis, you can take a graph that is these really long, stretched out hills and make them look like they're these really skinny, really tall, pointy things, and they're not at all, right? So labeling your axes can make it look different, but the graphs always look not the way they're supposed to. How about this one? This is another example where the period and how much you're horizontally shifting it by don't quite line up, but that's okay because there's actually a way we can still manage it. Okay? So as we go to label our axes, what is the period of this function? 2 pi. So whenever the period is 2 pi, you instinctively want to label the axes by pi halves. Agreed? But the problem is, if we take this graph, it's got a period of 2 pi, so here's one complete cycle, right? Then we horizontally squash it by 1/2, that's great. But then I have to shift it to the right pi thirds. Well, pi thirds ends up being right here, so I'm going to have a point here, and then a hill here, and a dip, and then... So none of my points are going to end up on the intersections of grid lines. Which we already did a problem like that, and that was fine, right? But is there a way I couldn't label these so that I get the best of both worlds? I get points that end up at both my helper graph and my final answer graph at the intersection of grid lines. If I label the axes by pi 6, that is perfect. Because pi 6 will cover the pi halves and the pi thirds. So if we call this pi 6, this will be pi thirds. What's this one? Pi halves. 2 pi thirds. 5 pi 6. Pi. And so on and so on and so on. Negatives. And what should I label my y-axis as? Yes, sir. No, just enough so that I can tell what you chose for the width of each of your squares. Where should I go for the y-axis? Halves. Okay? And that's it. That's great. Now, what I would typically do is I would graph the helper graph here. I'd probably graph, I probably wouldn't graph the parent. If you wanted to graph the parent graph would look like this. Okay, so that's what the parent, that is sine x right there. That's the parent function. I'm going to vertically squash that by 2. Okay? So this is what you'll get when you vertically squash it by 2. Whoa, missed it. And then we want to shift that to the right pi thirds, which is exactly 2 squares, right? Okay? So that red graph is really your final answer. Right?
So how does the function give us equations? Would they have the weird one that you showed us before?
So yeah, they could totally ask you something like graph y equals 3 sine 2x minus 7 plus 1. You have to rewrite that as 3 sine 2x minus 7 halves plus 1. You would have to do that. Yeah. Yeah, I will be giving you on tests and quizzes not factored out like that. Is that what you wanted? What's up? The red line is the green one shifted to the right pi thirds. So the red and green should look the same. It just shifted to the right pi thirds. Okay? What's up?
I don't understand like how the squash is like that.
If it's vertical, so here's what I do. Whatever this number is, that's your vertical stretch, you multiply the y coordinates by that number. Whatever the number in front of x is, you divide the x's by that number. That's the rules. Right? You always are when it comes to stretching, you're always dividing y coordinates by a. No, sorry. You're multiplying y coordinates by a. I'm sorry. Multiplying y coordinates by a. You are dividing x coordinates by b. And so because it's division, that's why you get that reciprocal effect. Because what is dividing by 1/2 actually the same as? Multiplying by 2. That's why it stretches it. Okay? If the number is a 5, you're dividing by 5, and that's why all the x coordinates get smaller and you see it squash in. Okay? Well, but this is a vertical. Verticals aren't backwards. You don't divide verticals, you multiply verticals. So that's a vertical squash by 2. You multiply the y coordinates by 1/2. So all the y coordinates get multiplied by 1/2. Okay? Let me show you another approach to this problem. Some of you might like this. I'm going to give you a grid with axes already drawn on it. Is there any rule that says this bold line has to represent y of 0 and this bold line has to represent an x of 0? In other words, do the bold lines, your axes, have to be your x-axis and y-axis? Could I make that bold line 5? Right? So what if we did it like this? What if I actually labeled my axes to where this this vertical line right here wasn't 0, it was pi thirds. Right? And then what if this point right here was whatever pi halves away from that is? What is pi thirds plus pi halves? 5 pi 6? And then what is 5 pi 6 plus pi halves? Yeah, I like the other way better as well, but you could totally do it this way. Yeah, it's harder, but, I mean, you could totally, well, you're not going to have your calculator. But what's 5 pi 6 plus 3 pi 6 is 8 pi 6, so 4 pi thirds. Right? And so on and so on and so on. So that way, I am able to incorporate my shift, but I'm using distances of pi halves because that is more conducive to what my period is, right? And so then, label this 1/2, negative 1/2, and you just go bam, 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 bam. Totally different looking graph, but because of the way the axes are labeled, it is absolutely correct. And I didn't do any helper graphs. I once did a whole quiz in high school because I was a smart aleck, where I drew the same exact graph for every single problem. Every single one. I just labeled the axes different. It's the same, it was literally like I had a photograph of every single same shape right in the middle of the axes, but I would just label the axes different. So the reality is, where is the origin for this graph? It's like somewhere over here. Okay? So that is another method you could choose to use. Just don't start at the origin. Start at whatever your horizontal shift is. You could do that. All right. As we are packing up for the day, let me show you what the graph of cosine looks like, because you'll be graphing cosine. Use your unit circle knowledge. What is the cosine of 0? 1. What is the cosine of pi 6? Radical 3 over 2. And so on and so on. So cosine is the same exact shape as sine, only it doesn't start at the origin. It starts at a hill. And it does not have origin symmetry. It has what we call y-axis symmetry. So this green graph right here every time I say green graph, I want to sing a Barney song about green grass. Green grass goes all around. That's right. That's embarrassing for you. Okay. So there you go. So, we've got some identities to add to our identities cheat sheet list. These are all identities we've already learned before. There's the odd-even identities. Because sine is an odd function, it has this identity. Yeah, all right, have a good one. Remind me to go over these new identities.